In exercise 923, we're going to think about catalytic hydrogenation from the perspective of synthesis, of hopscotching from the reactant straight to the product without thinking about step by step how everything happens in the mechanism. So here we're thinking more like chefs. What can we make out of these different ingredients? So in hydrogenation, you're adding exactly what it sounds like, hydrogen. Now hydrogen is diatomic. So one hydrogen atom, hydrogen is in group 1a, it only has one valence electron, and so it only needs one other hydrogen to come together and form a bond. And so that's H2. Now that's a gas at room temperature. There's a lot of fascinating stuff about hydrogen. The abundance of hydrogen in the universe. Hydrogen is the simplest element. It only has one proton in the nucleus with one electron going around it. The abundance of hydrogen in the universe is one of the pieces of evidence for the Big Bang, because the Big Bang was able to create a lot of hydrogen. All the other elements come from squishing hydrogen together, but that takes generations of stars. And in the universe, hydrogen is by far the most abundant element. When you see big gas clouds in outer space, hydrogen gas is what that is. Very tiny. I mean, everything else is a sort of garnish on that meal. Even when you look on our planet, you think about how much water is on the surface of our planet, and you think about the amount of hydrogen that's needed to make that water. You get a sense of how rich the hydrogen is. And it always bristles off of the backs of these carbon chains, like so many bristles in a brush. It's so ubiquitous, it determines acid and base chemistry, and it's a really fascinating compound. So here, what you would need is some sort of a metal for it to adsorb onto. And the metal can either be platinum, palladium, or nickel. So these are just sort of recipes handed down in the family of humanity. These are like humanity's family recipes handed down, finding that platinum, palladium, and nickel do this best. And they work by allowing both the hydrogen and the alkene to adsorb onto the surface of the metal. So this metal would look just like a chunk of metal to the naked eye. If you were to zoom in on it with a microscope, you would see that there are all these manifold caves and caverns, all of these holes and indentations and tunnels going through the metal that allows hydrogen gas to adsorb onto the surface. In other words, it has a lot of surface area. The hydrogen adsorbs onto the surface and sort of ice skates around it, each hydrogen atom separately. And at the same time, the alkene does the same thing. And eventually they knock into each other, and the hydrogens take the place of the double bond. Now I have this animated in a separate mechanism. The thing to note here is that they end up adding onto the same face of the alkene. So we get syn addition here, just like we got in hydroboration oxidation. Otherwise, these are often the simplest products to draw, because you really just need the same exact product as what you draw the same molecules what you started with. You just erase the pi bond, and that's your product. Now, technically, if you form a chiral center, which we don't in this problem, if you do, then you'll want to make sure you add the hydrogen's syn, and then adjust the other bonds to make sure that they're tetrahedral. So, excuse me, so for each of these you would want two bonds in the plane, one coming out of the plane, and one coming toward you. But because you don't have any chiral centers here, you don't have to indicate the stereochemistry, and it's enough to just erase the pi bond. The hydrogens that you add are implied. Okay, let's try another one. So we see an alkene. We know that we're going to do an addition reaction. What are we adding? You look at the recipe. We have hydrogen gas, flammable hydrogen gas, and with palladium. Well, draw the same carbon skeleton. The sigma bonds are not going to be affected. And see if you form a chiral center, because if not, then you're done. If you do form a chiral center, then you have to draw in the stereochemistry. But notice here we don't have any chiral centers. Even here, this carbon where the ring and the straight chain meet, that has the going around the ring in one direction and going around in the other direction are the same. So that's it's like being bonded to the same thing twice, and so it's not chiral. And so that's our product for that one. Technically, we removed the pi bond and added 2 hydrogens, but the hydrogens are implied in skeletal formulas. Okay, what if we do this? Well, you see an alkene, you know it's an addition reaction. You look at the recipe, it's hydrogen gas with a platinum surface. Catalyst helps the reaction happen faster. And so you redraw the same carbon skeleton, all the same sigma bonds, but you don't include the pi bond. So effectively you erase the pi bond. Now if you don't have a chiral center, then that's the end of that. That's the end of that story. If you do have a chiral center, then you have to draw the 2 enantiomers. And we do have a chiral center here. The carbon, now the only possible places it could be is the carbon in the ring or the carbon next to it. In other words, the carbons that were involved in the double bond. Those are the only ones that could become chiral. The one with the ring is in the same scenario as in the previous problem. Go around the ring in one direction, go around in the other. You run into the same stuff at the same point. And so those end up being like the same branch. So that's not a chiral center, because it's bonded to the same thing twice. Carbon can only be bonded to 4 different things, and they all need to be different in order for it to be chiral, for carbon to be chiral. For the other carbons, the other possible chiral center, we have an ethyl group, we have a methyl group, we have a ring, and the 4th thing is the implied hydrogen. That is there. And so that carbon is bonded to 4 different things, and so it's chiral. Now the original double bond, the pi bond, is flat. We discussed this before. Each carbon in the double bond is bonded to 3 atoms, has 0 lone pairs, so it's trigonal planar. Well, if this is trigonal planar and this is trigonal planar, this whole area of the molecule is going to be flat. Now that means that something that adds on to that surface has an equal likelihood of adding to one side as to adding to the other. And so you end up with a racemic mixture of the thing you're adding on each side, 50-50 mixture. So we'll draw in some stereochemistry for this. Let's say the hydrogen's added from the back, so that's going away. In that case, this methyl group would be coming out, because we need that tetrahedral center to have 2 bonds in the plane, one coming out and one going away. So that's one possibility. The other possibility, is that the hydrogen could have added to the front. And if the hydrogen added to the front, then the methyl group would be pushed so that it goes away. You'd have a 50-50 mixture of these 2 things. Now note, this is syn addition, so there is another hydrogen that we added here, and just to emphasize the fact that it's syn addition, the other hydrogen would have to add in that same direction. So if one hydrogen is going away, the other hydrogen would also be going away. If one is coming out, the other hydrogen would also have to be coming out toward you. Now in these skeletal structures, the hydrogens are implied, so you don't have to draw those. It was important to draw them so that we could correctly predict the direction of the methyl group, which we do need to draw. And so those are the 2 products. You'd get a 50-50 mixture of these 2 enantiomers if you did this hydrogenation reaction. The next one, you see an alkene, you think big category is addition. That's what I'm going to do with that. Not substitution or elimination, but addition. Look at the recipe. What are you adding? 2 hydrogens. The nickel is serving as a catalyst. So you can redraw that carbon skeleton just without the pi bond. Technically, you've added 2 hydrogens in. Now, if you don't have a chiral center, that is your product. End of story. But we do have a chiral center here, and the chiral center is either going to be on this carbon or the other one. You can see that it's not going to be on the one on the left because that has 2 hydrogens. That means that carbon is not bonded to 4 different things, and so it's not chiral. So it's the carbon on the right of the 2 carbons in the double bond. It's the one on the right that becomes chiral. Okay, well, we know that these add syn, so either the 2 hydrogens will add on the same side coming out, or they'll add both going away, but they have to add to the same side. Now, it doesn't really matter which direction this other hydrogen is going towards, because it's not chiral here. But I want to emphasize that the two hydrogens have to add syn, and that's why I wrote that in. We also want to make sure that the carbon that's tetrahedral and chiral is represented as tetrahedral, so it has two bonds in the plane, one coming out and one going away. Well, right now we have three bonds in the plane, so we have to make one of those, in this case, go away. So we'll have two in the plane, one coming out, and then we want that methyl group there to go away. Okay, well, we have that methyl group then going away, and there's that product. Okay, well, if on the other enantiomer, if the hydrogen is going away, that means this other group needs to be coming out at us. So we can have that as a solid wedge, and that's coming out. So those are our two enantiomers. Now that we have those drawn in, we can erase the hydrogens which are implied in the skeletal structure. And these would be your two products. You'd get them in an equal 50-50 racemic mixture if you did this hydrogenation. Okay. For E, you see an alkene and you think addition. You can do an addition reaction with that. Right? You don't have any leaving groups, so you wouldn't do substitution or elimination. But you do have those extra electrons, that extra molecular glue you can use to add something, stick something onto that carbon chain. So you're doing addition, you look at the recipe to see what you're adding, and you see H2. So you're adding two H's, you're doing hydrogenation. So you can redraw that same molecule, but without the pi bond. Now if you don't have any chiral centers, you're done. And here we don't have any chiral centers. The only two carbons that could have been chiral are these carbons on the end, and they're both bonded to the same thing twice. They both have methyl groups. They're both bonded to two methyl groups. That means that they can't be bonded to four different things. And so neither of those carbons are chiral, and that's your product. With hydrogenation, if you don't have any chiral products, if your product doesn't have any chiral centers, then you can really just erase the double bond, and the hydrogens that you add will be implied in the skeletal structure. Okay. Similar thing here. You see an alkene, and you think, okay, the big class of reaction that I can do with this is addition. What am I adding? You look at the recipe. You see H2 and palladium. Palladium is acting as the catalyst. It's going to let the hydrogen adsorb onto its surface, sort of ice skate around it, until it knocks into a molecule of the alkene that is also adsorbed onto the surface. So it's like a hub, a meeting place, a coffee shop where the hydrogen and the alkene run into each other. So it catalyzes the reaction. We're going to add two hydrogens, and we're going to add them syn. They're going to go on the same face of this carbon chain. So start by drawing the same carbon chain, just erasing the pi bond. Now if we don't have any chiral centers, then that's our answer. But here we do have chiral centers. We have two of them. Both of the carbons that were in the double bond are chiral centers. They have an ethyl group attached to them, and actually it's the same for both of them, an ethyl group attached to them, a methyl group attached to them. They have each other attached to them, and then they each have a hydrogen. So that's four different things. The hydrogen here, and just... So that's four different things on each of them, so they're both chiral centers. Well, if they're both chiral centers, we have to draw the two enantiomers. So we're going to get two versions of this molecule. Now either the hydrogens have to add syn. That's one of the things that happen in hydrogenation. So either they're both going to be coming out at you, in which case, to make the carbons that they're on tetrahedral, you'd have to replace the methyl groups, or not replace them, you'd have to push them so that they're going away, or the two hydrogens will add going away on the backside, in which case those methyl groups would become solid wedges. They would get pushed to go toward you. So those are the two possible products. Let's just erase our hydrogens because those are implied in these skeletal structures. Those are the two possible products, the two you'd get a racemic or 50-50 mixture of those two enantiomers, equal mixture of those two enantiomers in your product if you did this hydrogenation. So hydrogenation is often the simplest, one of the simpler products to predict, because you're really just erasing the pi bond. The hydrogens that you add are often implied in your drawing. However, just keep in mind that the two hydrogens have to add syn. And so if you create chiral centers, you will only create chiral centers that are created by the syn addition of the two hydrogens adding on the same side of the double bond.